theory and duality. And it will be about some Chern-Simons-like TQFTs in 3 dimensions that appear by reduction of the 6D superconformal 2,0 theory, or equivalently that appear on the topological side of the 3D correspondence. A lot actually is already known about this series, so one might think that like almost everything that you would like to know. There are explicit reductions from 6 dimensions that obtain this series, and there are state integral models that compute partition function of this series on large classes of 3 manifolds. But in fact, a number of properties of this series seem puzzling, and I would like to argue that some of these puzzles can be explained by S-duality and properties of the Kapustin-Witten equations. So let me start with a brief review of the 3D correspondence. We take the 6D 2,0 theory, and these series are labeled by AD idempotent diagrams, and for simplicity I will restrict to the case of A1. So this is a theory on 2 M5 branes. The theory is put on a product 6 manifold, which is some 3 manifold with times some other 3 manifold, with a particular supergravity background that preserves at least 2 supercharges. So here M3 is it can be any smooth and oriented 3 manifold, and L is a 3 manifold that must admit some extra geometric structure for the supergravity background to exist. I will restrict to the case when L is a degree K circle bundle over S2, so it will be S1 times S2, S3, or case length space. And I will sometimes denote it LKB to specify also a complex parameter B of the supergravity background on which things depend. The 2 factors in the product are not on equal footing. So along M3, the theory is topologically twisted, and supersymmetric observables are expected to be independent of the metric on M3. But they do depend on the background on this length space through this parameter B. So here is our 6D theory, and if we reduce it on M3 down to 3 dimensions, we get a 3-dimensional n equal 2 superconformal field theory labeled by M3. It's called T of M3 on this squashed length space. And so this T of M3 is a topological invariant of M3, which is valid in quantum field theories. But it's not very easy to construct this series explicitly. For M3, which admits ideal triangulation, there is an algorithm for building a candidate theory, TDGG of M3, proposed by Dimofte, Gayota, and Gugov. And it is known that in general, this TDGG of M3 describes only a subsector of the full theory, and we are not entirely sure that the full T of M3 even exists as a superconformal theory in 3 dimensions. But there are examples where the full of T of M3 was proposed. Literature. Anyway, we will focus on the other side of the 3D correspondence, which is when we reduce on the length space. Then we get a Chern-Simons-like TQFT on M3 with coupling constants which are determined by K and the NB, the parameter of the background. The theory that we get in this way, it is known to be SL2C complex Chern-Simons theory. SL2C because I'm taking A1 theory in 6 dimensions. And SL2C Chern-Simons theory has an integer level K, which is just the degree of the circle bundle, and a complex value level V, which is determined by the supergravity background parameter. So this theory was obtained from 6 dimensions for K equal to 1 by Kordov and Jafferitz, and there are papers which obtained for K equal to 0, and also it was checked by Dimofte in this paper. And part of the statement of the 3D correspondence is that the partition function of T of M3 on the length space and complex Chern-Simons on M3 are equal. Okay, let's further restrict to K equal to 1. So now our LKB is just a squashed 3 sphere. And the TQFT is complex Chern-Simons theory at integer level K equal to 1. Interestingly, before Kordov and Jafferitz obtained this theory from 6 dimensions, it was thought that the correct TQFT is actually SL2R Chern-Simons theory, not SL2C Chern-Simons theory. And the reason is the following. So suppose we take our TQFT on M3, which is a product R times a surface. And then we may ask what is the space of states that our TQFT associates to C. And this is just the space of BPS states of the 6D series on R times C on S3. And if we reduce on C, we get a 4D n equal 2 plus S series T of C, which people know from the AGT correspondence. And part of the statement of the AGT correspondence is that the space of BPS states of this series on squash 3 sphere is a space of Liouville conformal blocks at central charge determined by B. And it has been known since long ago that Liouville conformal blocks arise as a Hilbert space in SL2R, or more precisely SL2R-like Chern-Simons series. And one goal of my talk will be to explain what this SL2R-like Chern-Simons series really is and why it is related to SL2C at level 1. So I also mentioned that there are state integral models that compute partition functions of this series. So if M has non-empty boundary and admits an ideal triangulation, then there are several versions of state integral model that compute the partition function. And the idea that to each tetrahedron in the triangulation of M3, one associates a quantum dilogarithm of a local holonomy variable. And then gluing those tetrahedra corresponds to symplectic reduction in the space of flat connections, and it is implemented on these wave functions by integration and setting some variables to 0. But since Hilbert spaces of complex Chern-Simons series in general are infinite dimensional, the partition function need not be finite on any 3 manifold. Like, for example, on S1 times C, it is a dimension which is infinite. And in these state integral models, we have the problem of convergence of the integrals. And there is a universal prescription of integration cycles for M3, which admits a positive angle structure. Then there is a canonical integration cycle on which the integral converges. And this state integral model is well defined for this parameter B with real part positive, or equivalently for B squared in C with negative real axis thrown out. So, for example, for k equal to 1 and the figure 8 not complement, the partition function is given by this integral. So here psi b is the quantum dilogarithm, and we have 2 of them because there are 2 tetrahedra in a triangulation. And this integral implements symplectic reduction. So this partition function has interesting perturbative expansions in different regimes. Like, for example, if we take b squared going to infinity, it goes like e to the minus b squared times the hyperbolic volume of the knot complement. And there is a similarly looking formula at b squared going to 1. Then there is a finite term, and then there are terms which are order epsilon. And also when b squared goes to minus 1, then there is a similar expansion, but here we have oscillating exponentials, so there is no smooth limit. And these combinations, p over 12 plus minus hyperbolic volume, are just Chern-Simons invariants of the 2 reducible p equal to C flat connections in the complement. So in this formula, the asymptotics at b squared going to minus 1 is what we would expect from the Cordova-Jaffer's Chern-Simons series that I mentioned. That is a semi-classical limit. But the other 2 regimes are not so clear from there, and I will explain what series they correspond to. So next, let me give a very quick derivation of these Chern-Simons series from 6 dimensions. So this is a derivation that is kind of alternative to what Cordova and Jaffer's did, and it is very simple, and it will help to elucidate some properties of this series. So optimally, we would like to start with a 6D supergravity background and reduce on the length space to 3 dimensions. But I do not have an explicit description of this background. So in 5D, there is a background that was used by Cordova and Jeffers, but it's not quite as general as I need for this argument. So instead, let's take the size of M3 to be very small, so that our 6D series really just becomes a 3D n equal to series in the remaining 3 dimensions. And then we know how to put a 3D n equal to series on a squashed length space, so there is a nice background. And this background has some nice features, which we will assume to hold also for the 6D background. And just from that, we can easily get our complex Chern-Simons series. So we can view the length space or a three sphere as a torus with coordinates phi1 and phi2, which is fibered over an interval, with some cycle of the torus shrinking at one end and some cycle shrinking at the opposite end. And depending on which cycle shrink, we get three sphere or length spaces. And to put a 3D n equal 2 theory on this background, we need to specify some geometric structure on this length space. And this geometric structure is a metric and an integrable transversely homomorphic filiation compatible with this metric. So let's choose the metric like this. So this is just a torus fibered over an interval where the area and the modular parameter depend on y in an arbitrary way, with only constraint that a is positive and im tau is positive. And also there should be some conditions at the ends of the interval for the metric to be smooth. So to specify a THF compatible with the metric, it is enough to pick a unit vector field. So the idea that we essentially define complex structures on the planes orthogonal to this psi, and we define them such that the metric in those orthogonal planes is Hermitian with respect to this complex structure. So it is enough to have psi. And we take an arbitrary combination of three unit field-buying vectors with some coefficients which are parameterize the point in S2, and we use a projective coordinate T of y to parameterize this. So this determines a THF which is compatible with the metric, but it might not be integrable. In fact, for it to be integrable, it is integrable if there exists a constant psi, such that t squared is related to tau and psi by this formula. So this psi, which can be complex or infinity, is a u and y independent parameter. And explicitly in this THF, the local holomorphic coordinate in transverse fibers is given by this formula. The formula above fixes t in terms of tau and psi up to a sign. And there are two branching points at tau equal to psi and tau equal to psi bar. That will be important. And this 3D n equal to background preserves two supercharges of opposite R charge, which anti-commute to translation by a complex scaling vector determined by psi. So you can think of this as an omega background. So if you take q plus h q tilde, you will have epsilon 1 d phi 1 plus epsilon 2 d phi 2, where psi is epsilon 1 over epsilon 2. So it is known that the partition function of a 3D n equal to theory on such background does not depend on all details of the geometry. In fact, when we change the geometry, it only depends holomorphically on the Dolbeault homology class of the THF deformation. And one can show that in our setting, any changes in A of y, t, tau of y, or t of y for fixed psi lead to trivial, that is Q exact deformations. So the partition function depends only on the geometry as it has only homomorphic dependence on psi. And you kind of can see it from here, that if we change anything but keep psi fixed, what changes in the homomorphic coordinate is its integral, and we can absorb this change into a redefinition of y, so that does not really change the complex structure. So let's assume that the 6D lift of this supergravity background has the same nice property that we can change the area and the modular parameter arbitrarily while keeping this parameter psi. So then we can take the torus fiber to be very small and reduce on it to 4 dimensions. And we get 4D and equal 4 super Yang-Mills on M3 times this interval, which was our y coordinate in the length space. And the modular parameter will obviously become the gauge coupling, and since it in general depends on y, we have a Janus configuration. And then a PQ shrinking cycle at an end becomes a PQ5 brane boundary condition in the n equals 4. So it is also easy to see that this T of y, at least when it depends on y slowly, it becomes a Kapustin-Witten twisting parameter. So this n equal 4 super Yang-Mills comes with a Kapustin-Witten twist that was used in their Langlands paper. And so this T of y becomes their twisting parameter. And then the formula for T squared in terms of psi and tau really is a formula for psi in terms of tau and T, which is known from their paper. So, and obviously n equal 4 super Yang-Mills twisted partition function depends on psi holomorphically, but does not depend on tau and T, because those are Q-exact deformations. Note that here we've chosen the basis of cycles on the two torus, and if we change this tau and psi, transformed by Möbius transformations, which is 4DS duality action. Now, let's specify to the case k equal to 1 again, so we have a squared 3 sphere, and take the background, the basis where 1, 0 cycle shrinks on the left, and 0, 1 on the left, and 1, 0 on the right. Then with this choice, one can show that psi is equal to b squared, where b is the usual parameter by which people parameterize squared 3 sphere backgrounds. So, and here we have a plane, tau plane, so tau is some function that depends on y, which goes to plus I infinity on one end and 0 at the other end, and here it goes along some curve which does not matter, as long as it is in the upper half plane. And so there are 2 points, psi and psi bar, which are important. And remember that tau equal to psi or tau equal to psi bar was branching points for t squared. So we can move everything around, but these points should not cross this contour. So really, these backgrounds are well defined for any p squared, which is not on the negative real axis, because then we would pinch this contour and force im tau to be 0 somewhere. So this background is well defined, in fact, for the same values of p squared, for which De Morte's state integral model is well defined. So we used this basis of one cycles, but there are 3 other useful choices of one cycles, or equivalently as duality frames in the n equals 4, which give some sorts of Chern-Simons series. So they are related by as dualities. In duality frame 1 and 2, as I will explain, we get something like SL2R Chern-Simons series, which should more properly be called Teichmüller TQFT. And in duality frames 3 and 4, we get complex SL2C Chern-Simons series, and number 4 is a series found by Cordova and Jeffers. So next, let's look at this series in more detail, starting with Teichmüller. So in this duality frame, we have Langlands twisted n equal 4 with a D5 boundary condition and NS5 type boundary condition at the 2 ends, y0 and 1. And for this part of the talk, I will strict to b squared being real and positive, which is where the theory can be understood most explicitly. So the field content of this series, the usual Kapustin-Witten Young-Mills field content, which is a gauge field, which is a SO3 connection on a principal bundle E over the 4 manifold M3 times I. And a one form, which is adjoint valued, and it comes from 4 out of 6 scalars of the 4D n equal 4 super Young-Mills after twisting. And there are also 2 or one complex adjoint valued field sigma and sigma bar, and some fermions, but for the most part they will not be important. The bulk part of the action is almost Q-exact, and these Q-exact terms serve to impose localization onto the Kapustin-Witten equations, which are these equations. So F is the curve which are for this gauge field, and this is gauge covariant Dirac derivative and 4D Hodge star. And we took T, so the Kapustin-Witten equations depend on T, and we took T equal to -1, because that will be convenient. So let's choose the gauge AY equal to 0, and then also note that component phi y of the one form along the interval. It vanishes at both ends of the interval as a consequence of the boundary condition. And then a simple integration by parts argument for these equations show that phi y vanishes everywhere. So then Kapustin-Witten equations reduce to flow equations in Y for a connection and a joint valued one form on M3, together with some equation for phi. And these are sometimes called reduced Kapustin-Witten equations. So I will denote by omega curly A of M3 the space of complex SL2C gauge fields on M3, and these equations, the top 2, are just the gradient flow for the minus imaginary part of the Chern-Simons functional of this curly, of the complex A. And this is the basis for the starting point for Witten's story about analytic continuation of Chern-Simons theory. So to be more precise, the bulk part has not only Q-exact terms, but also a topological term which is proportional to the canonical parameter of psi. But we will treat it as a boundary Chern-Simons term. So it combines with some terms at the NS5 boundary into this action. So this is supported at y equal to 1, and this becomes a complex Chern-Simons action of this complexified gauge field. So this A is A plus I5, which are just restrictions of the bulk fields onto this y equal to 1. So now the D5 boundary condition is what is known as the numpole. So what it does, first of all, it identifies the gauge bundle with the tangent bundle of M3, and also the fields are required to behave according to this model singularity. So phi has a 1 over y singularity as y goes to 0. And here E and omega are the field bind and the Levi-Civita connection of the metric on M3. So this boundary condition ties together the metric geometry of M3 and the gauge bundle. And the dots here stay for higher order terms. So since we identified TM3 with a joint bundle, omega and E can be viewed as a connection and enjoy value 1 form, so this formula makes sense. This is a nice boundary condition for the Kapustin-Witten equations, despite the fact that it is singular. So it solves the equations to all singular orders, and also it is elliptic in the sense that the linearization of the Kapustin-Witten equations gives a Fredholm operator between suitable function spaces. So this is a nice boundary condition. Also, it breaks all the gauge symmetry at the boundary, so there are no problems with reducible connections. Now, so I'm claiming that this theory is Teichmüller TQFT, and let me explain why and what this is. So for that, let's take our M3 to be 2-manifold C times R, and we want to see what is the Hilbert space that the theory associates to this Riemann surface. So if we reduce on C, we get a two-dimensional sigma model on R, which is time times interval, which is this interval, which is the Hitchens model, the target is a Hitchens moduli space. And since we took T equal to -1, it is an A model in complex structure K. I'm using the usual notation from Kapustin-Witten, say. So the symplectic form is a multiple of omega K, and there is a B field here, so which is proportional to omega I. And then the NS5 boundary condition at y equal to 1 reduces to the BAA canonical coisotropic brane, whose support is the whole MH, and its physics is governed by a holomorphic symplectic form, which is just omega K minus I omega I times B squared, which is B squared times omega J. So you can see this is essentially a reduction of the symplectic, comes from the Chern-Simons section on the NS5 boundary. And the D5 boundary condition reduces to a BAA Lagrangian brane, which is supported on the Hitchens section. So this is a fact about moduli space of solutions of Kapustin-Witten equations with a numpole. So it is explained in these papers and proved mathematically. The Hitchens section is a component of fixed point set of an I-holomorphic involution on A and phi. And this Hitchens section is, in fact, topological just R6G minus 6, where G is the genus of C, and it is isomorphic to the Teichmüller space. And the imaginary part of this holomorphic symplectic form reduces on this Lagrangian brane to a multiple of the Bethe-Peterson-Keller form of the Teichmüller space. So our brane configuration is, in fact, an example of the usual story of branes and quantization setup of Gukov and Witten. So we have a coisotropic brane and a Lagrangian brane, and then that serves to quantize the support of the Lagrangian brane with symplectic form, which is the imaginary part of this thing. So we are quantizing Teichmüller space, and the wave functions that we get from this are known to be Liouville conformal blocks of central charge determined by B squared. So that's why this theory will be called Teichmüller TQFT. Now let's get back to 3 dimensions. So can we understand the theory there? On a general M3. So we are supposed to solve the reduced Kapustin-Witten equations of on this interval with the numpole boundary condition and a free boundary condition at y equal to 1. And then if we evaluate Kapustin-Witten solutions at this end, we get some subspace in the infinite dimensional space of complex gauge fields. And this subspace informally is middle dimensional because the non-pole boundary condition is elliptic, so it restricts 1/2 of the mode. Yeah, it's also like it's a real middle dimensional cycle. So we can integrate the top dimensional homomorphic form over this cycle. And then the path integral really just reduces to an integral over the space of what we had on the NS5 brane, which is the Chern-Simons section. So we get some analytically continued Chern-Simons path integral over this cycle S. Can we understand this integration cycle? Well, so first of all, for the path integral to converge, we need the real part of the argument of the exponent to be bounded from above on the integration cycle. This is a non-trivial conjecture about Kapustin-Witten equations, and I don't have a proof, but we expect this to be true when the Teichmüller TQFT partition function is finite. Assuming this to be true, we can decompose S into left-shift symbols for critical points. And critical points here are flat connections on M3. So I will, for simplicity, assume throughout this talk that all flat connections are isolated. So, for example, you can think of a knot complement and roots of the A polynomial. And importantly here, in this sum, only irreducible flat connections on M3 appear. You can see this by carefully keeping track of gauge invariance in those Kapustin-Witten equations. So the sum over irreducible connections. And also these critical points are not just flat bundles modulo all gauge transformations. So these are flat bundles modulo topologically trivial gauge transformations, because here B squared is not integer. So critical points, different lifts of Chern-Simons action from C mod Z to C are different critical points. So these are essentially a flat connection and an integer, which is like floor of the real part of Chern-Simons. So the partition function decomposes in the same way into integrals over left-shift symbols. And remember that semi-classically at B squared going to infinity, a left-shift symbol integral behaves it has just this leading semi-classical term. So to find these decomposition coefficients n, we take the cycle S and push it down with the gradient flow and count the number of times that it hits some critical point. So NA is the number of flows that start from our cycle and go to some critical point A. But since our integration cycle itself was defined by downward flow from the numpole, we can just count flows from the numpole to critical points. So that is what these ends are. And in fact, this counting problem for the Kapustin-Witten equations is what appears in the conjectural S-dual description of the Witten-Rashtikin-Turai for analytically continued Chern-Simons invariance of M3. So this counting problem is something known. But it's not known how to make precise sense of them because of compactness issues with Kapustin-Witten moduli spaces. But, well, physically this should make sense, and we'll optimistically assume that it works. So now suppose that M3 has a complete hyperbolic metric. Then the integration cycle can be understood very explicitly. So Anderson and Kashaev looked at those state integral models, and they observed that for hyperbolic knot complements, when B squared goes to plus infinity, the partition function goes as e to the minus B squared times volume. I showed this for the 4-1 knot, right? Here, this formula. And this is similar to the volume conjecture for the Jones polynomial, with the crucial difference that there is a minus sign, so it is suppressed, not growing. And we believe that similar asymptotics hold for any hyperbolic M3. And if we run this story for SUN instead of SU2, then for n going to infinity, we can support this by a holography argument. Recall that on a hyperbolic 3 manifold, there are two special flat connections, PSO2C flat connections, which are made from the Levi-Civita connection and the Hilbert. So they are flat as a consequence of curvature equal to -1. And Chern-Simons invariant, I will call them geometric and conjugate geometric. So Chern-Simons invariant has imaginary part proportional to the volume. And it is known that for any flat connection, imaginary part of Chern-Simons section is bounded by the volume on both sides. So, and I will assume that the equality holds only for these two special connections, which should be true generically. It means, all this means that the exponential that we see in Teichmüller partition function is the most subleading one. So if this integration cycle S contained any critical points besides the conjugate geometric critical point, we would not see this exponent. So it must be the left symbol. In fact, for a unique lift of this connection, because there are no oscillating prefactors. So this implication of the Anderson-Kashaf conjecture for the integration contour was considered before. So equivalently, it must be that all these ends are 0 except 1 for the conjugate geometric connection. And interestingly, for any hyperbolic M3, there exists a very simple model non-pole solution to the Kapustin-Witten equations, which is just this. So it is a simple ansatz proportional to omega n e and a factor that depends on y in phi. And it obviously satisfies the non-pole boundary condition because this is 1 over y, and at infinity it approaches precisely a conjugate geometric flat connection. So we make a conjecture that for a hyperbolic M3, the Kapustin-Witten equations with t equal to -1 with a non-pole have precisely one solution that approaches an irreducible flat connection at infinity. We have nothing to say about reducibles because they don't contribute to Teichmüller anyway. And the only solution should be this one. I don't have a proof, but there is an argument how something like this could happen. So let's look again at this functional and on the model, or we can evaluate it on the model solution. Then it's just some function of y. And let h of y be evaluation of this h on some other arbitrary solution at y. So the conjecture that for the same setup, but for the reduced Kapustin-Witten equations on M3 times R plus, any solution other than model solution lies below the model solution at every y. If this is true, then no other solution can convert to a flat connection at infinity because all other flat connections lie above the conjugate geometric connection. And we are careful here. So in fact, this is true for reduced Kapustin-Witten equations, but not for the full equations. And that in fact does not, so that subtlety does not prohibit approaching a reducible flat connection at infinity, which would be too much to ask for. And also, this is only for t equal to ±1, of course. So to illustrate, let's take a simple ansatz for the fields. So this ansatz sees only two critical points, geometric and conjugate geometric. And this is the profile of H, which becomes a polynomial in two variables. So non-pole solution means that we descend from this hill. The solution that goes along the ridge is the model solution. So what we say is that every other solution slides faster, and that can be easily proved for this ODE. And for the full system of Kapustin-Witten PDEs, I tested this conjecture by solving equations perturbatory in Y, and this inequality holds at least to the first two non-trivial orders. But I don't have a proof of the full thing. Okay, so now some final quick remarks about Teichmüller. Sometimes it is said that the space of Liouville conformal blocks is the Hilbert space of PSL2R Chern-Simons theory. And why is that? That's because PSL2R flat connections decompose according to the Euler number. And the top component here are precisely flat connections that come from the uniformization. So the top component is the Teichmüller space. So in a geometry like R times C, the phase space of Teichmüller is just a component in the phase space of PSL2R. Equivalently, the Hilbert space of Teichmüller is a subspace of PSL2R. So we really can just project onto it by putting some boundary conditions, and then the Teichmüller is just a subsector. But on a general three-manifold, it's not clear how you could project from PSL2R to Teichmüller. So PSL2R has more lines. And so these are just different series, and also the critical point that contribute to the path integral in Teichmüller are not PSL2R flat connections, but rather the geometric flat connection. So this Teichmüller is in a sense, chiral gravity, although it is a TQFT, not gravity. So, and second remark is that suppose we look at the M3, which has a boundary, which are some surfaces of negative Euler characteristic. So suppose this M3 has a hyperbolic structure, then it in fact has one hyperbolic structure for every choice of conformal structure at infinity on this boundary. And so there is a natural geometric flat connection for any point Q in the Teichmüller space of the boundary. And then a natural guess, a natural extension of the Anderson-Kazhaev conjecture would be to say that integral of the left symbol for this guy computes Teichmüller TQFT partition function on M3 in Kähler quantization. So it is a holomorphic function of this Q in the Teichmüller space of the boundary. And the reason is that fixing conformal structure at infinity is equivalent to putting a brane of opers into this Teichmüller TQFT setup. So here is Teichmüller brane, isotropic brane, and then we add a brane of opers. So this brane creates this holomorphic state. So one well-known example of this Teichmüller setup is when this M is a handle body with a network of monodromy defects, and then this setup is just holographic setup for conformal blocks. So this is nothing new. Okay, so now we can come to the duality. So we looked at these particular duality frames. Now let's apply S-duality, the basic S-duality element together with some reflection just for convenience. Then we get, again, Teichmüller TQFT, but with B going to 1 over B, and this is the usual symmetry B to 1 over B in the Liouville theory. So in the state integral model, this is manifestly present. So this kind of gravity, chiral gravity theory has this S-duality where you take B to 1 over B. This was actually discussed by Dymov and Gukov, although they didn't quite explain that the theory that they have is Teichmüller TQFT. Now, in duality frames 3 and 4, we have complex Chern-Simons series because we have NS5 boundary conditions on both ends. And 1, 0 is NS5, and 1, K is NS5 with an extra level K Chern-Simons term. So both of these lead to complex Chern-Simons theory, where the coupling of this CS of A is just minus psi, because it comes from the bulk Chern-Simons term, and coupling on the right is psi, but shifted by K on the brane. So from this we get K and V for these two Chern-Simons series, and here we get the answer that Kordov and Jaffer's had. So let's identify the integration cycles in this complex Chern-Simons series. So in what I called CS3, which is a series different from Kordov and Jaffer's, we have some puzzle. So the squashed three-sphere background and Teichmüller TQFT and state integral model, they all are well defined in the neighborhood of B squared equal to 1, so it's analytic. But this theory has semi-classical limit when B goes to 1, psi goes to infinity. So normally you would not expect Chern-Simons theory to have a smooth limit when the level goes to infinity. But that is for the usual integration cycle. But for an unusual integration cycle, something like this can happen. So let's expand the integration cycle in terms of Lefschetz symbols. And here the sum also goes only over irreducible connections. That is the usual fact about complex Chern-Simons theory, because a reducible flat connection, its contribution should be divided by the volume of the isotropy subgroup. And isotropy subgroups are complex and their volumes are infinite. So reducible flat connections on a finite volume 3 manifold never contribute in complex Chern-Simons. So let's find this ends. The absence of essential singularity and at psi equal to infinity imply the following conditions. First, the coefficient in front of psi here, which is minus Cs of A plus Cs of A tilde, should be 0 at every critical point. That is not entirely obvious because you could think that maybe it is just the real part is of psi times this thing is always negative, so it's always decreasing at every Stokes chamber. But in fact, you cannot reach that. So a Stokes phenomenon will always create an exponentially growing contribution if you have non-zero action in some Stokes chamber. So this was explained by Witten. So then this n can be non-zero only for A equal to B. And also this nice property of n should not be spoiled by Stokes phenomena as we go around psi equal to infinity. And assuming that Stokes jumps are generic, that in fact implies that NAA is equal to NBB, then Stokes jumps will cancel. So that fixes the integration cycle uniquely up to an overall coefficient. And this is a diagonal sum over reducible connections, but it's not the usual integration cycle. In the usual integration cycle, we would have CA times CA bar. And it turns out that Stokes phenomena also cancel for this combination of Lefschetz symbols for B squared positive. So in the same region where Teichmüller TQFT is well defined. So on this line, we still understand the integration cycle. It is valid along this real line. And in terms of Chern-Simons couplings, this is where V is imaginary. So this is what was called like the second unitary branch of complex Chern-Simons theory by Witten back in the 90s. So let's see. So since the partition function is finite at psi equal to infinity, let's look what it is. So obviously, all perturbative coefficients beyond one loop vanish because the coupling is 0. So it becomes just a one-loop formula, torsion squared times the classical action, which comes from this -1. Sorry, 4 pi are wrong here. So and tau A is a Raysinger torsion for a flat connection. So for example, for a figure 8 knot complement, that state integral of Garofalidis and Kashaev gives this formula. So this is precisely what we would expect. So these are two critical points. In fact, on the 3D dual side, this equation is nothing but the formula for around the 3-partition function, which is a special case of what these people derived. So it is a sum over beta vacua of Handel gluing operator times the fibering operator, because S3 is degree 1 bundle over S2. So, and since this formula extends to all orders in psi -1, in fact, we can write a similar formula for perturbative expansion of S3 partition function in B -1. And of course, I should note that B equal to 1 is a round 3-sphere partition function. So in a round 3-sphere on the 3D dual side, we have classical Chern-Simons theory. Okay. Now, the integration cycle for the Cordova-Jaffer's theory was predicted in their paper to be the usual one. And in fact, one can also guess it from this picture because of this -1. So this is the usual integration cycle, which makes sense for real V, which is B squared lying on the unit circle. And then the partition function has an essential singularity at B squared -1, but that is okay because our supergravity background is not well defined for negative B squared. So, and the numerical experimentation show that indeed at B squared equal to -1, say for this knot, we get this formula, which is the semi-classical expansion. So let me conclude. So here in the B squared plane, we have 4 different descriptions of this Chern-Simons theory. When B squared is real, we have 2 different Teichmüller TQFTs and Chern-Simons number 3 with the unusual integration cycle. And this is central charge lying greater or equal than 25. And at C equal to 25, we have semi-classical limit in this CS3. On the real circle, or on the unit circle, where C between 1 and 25, we have this other Chern-Simons theory with this usual integration cycle. Of course, all these theories are should be defined everywhere, but we just don't know the integration cycles. So there are many interesting questions that one would like to understand. Like, for example, understand these dualities at the level of mirror symmetry in the Hitchens sigma model. So, for example, what are states in this unusual Chern-Simons theory? Is it the quantization of MH with some real symplectic form? Also, Teichmüller TQFT is unitary, so how do we see unitarity in this CS3? At C equal to 1 and C equal to 25, we have those semi-classical limits, which mean that Liouville conformal blocks at those values of C are, in fact, states in a B model with 2 space-filling BBB branes. So what can we learn from that? Also, Teichmüller TQFT on an interval with upper boundary conditions, in fact, reduces to Liouville. So there should be a duality between Liouville and 2 kind of complex K equal to 1 WCW models, one of which can be naturally continued to C less than 25. So what are these models? And then finally, we focused on K equal to 1, but K equal to 0, for example, and K equal to 2 are also interesting. So there are interesting dualities for these values. So it would be good to understand them.